In this video, we are going to talk about feasibility in linear programming, and also we will discuss about a situation where we can have multiple optimal solutions. An organization is producing two qualities of paints, paint A and paint B, and the profit value on these paints are given as 500 units per liter and 800 units per liter. These paints require different chemicals like chemical L, M and N, and the requirements of these chemicals in these paints are given. Paint A per liter requires chemical L in 30 units, chemical M in 40 units and chemical N in 25 units. Similarly, paint B per liter requires chemical L in 50 units, chemical M in 30 units and chemical N in 20 units. These chemicals are available in 1500 units per day, 1200 units per day and 1000 units per day quantity respectively. So when the organization produces these paints, obviously they want to maximize the profit, and at the same time the consumption of the chemicals L and M cannot exceed the quantity available. So we will formulate the linear program, and then we will further discuss about the feasibility and optimality there. We are going to create two examples of feasible solutions for this given problem, and also we will create one example in which chemicals M and N are available but L is short, and then we will look into the optimality, and we will try to change the profit value of paint B to get multiple optimal solutions with paint A quantity being greater than 15 liters per day. So this is what we are going to do. So let us first formulate the linear program. Since profit on paint A is 500 units per liter, so if we produce X units of paint A per day, then the profit from paint A will be 500x. Similarly, if Y is the quantity of paint B produced per day, and since the profit on paint B is 800 rupees per liter, so 800 into Y, that gives the profit from paint B. So the total profit will be 500x plus 800y, and that we will be maximizing through this linear program. Looking into the constant, chemical L, the consumption of that will be 30x for x liters of paint A and 50y for y liters of paint B, because 30 and 50 are the requirements of chemical L in paint A and paint B respectively. So 30x plus 50y is the total consumption of chemical L, which has to be less than equal to 1500, which is the availability of chemical L per day. Similarly, for chemical M, if we take the requirement of chemical M as 40 and 30 in paint A and paint B respectively, then 40x plus 30y is the total consumption, which is less than equal to 1200, which is the available quantity. Similarly, 25x plus 20y less than equal to 1000 gives us the constant for chemical N. And since paint A and paint B, the quantity of these to be produced per day has to be greater than equal to 0, means either we don't produce or we produce. The value of x and y cannot go in negative, so that's why x and y both greater than equal to 0. So this is the complete linear program where the objective function is 500x plus 800y, which is to be maximized, and the constants, the three technical constants are given here, and non-negativity constants are here. Now to find out two such solutions which are feasible, uh, one way can be that we take some value of x and y, and we check all the constants and see if those constants are satisfied, then that solution is feasible. Another way may be that we draw the feasible solution space and then try to attempt all the three problems which we have discussed in the beginning. So here is the graph using which we have drawn the feasible solution space. The three constants which we have: chemical L constant is 30x plus 50y less than equal to 1500. But to get the feasible solution area, we will be drawing the straight line of 30x plus 50y equal to 1500, and see which part or which side of that straight line gives us 30x plus 50y less than equal to 1500. So to draw the line, we have already drawn the lines here in the graph, and as you could notice that this is the L line which is giving us 30x plus 50y equal to 1500. Similarly, this is the M line which gives us 40x plus 30y equal to 1200, and this line is the N line which gives us 25x plus 20y equal to 1000. To draw the lines, it is simple. You need to have any 2 points on the line, and then you can draw that. So one simple way is that you can substitute the value of x as 0, and then you can see that 50y will become 1500, so y is equal to 30. So x equal to 0, y equal to 30 will be a point. So x equal to 0 and y equal to 30 is this particular point. Similarly, if you substitute y equal to 0, then x becomes 50. So x 50 and y 0, that is the other point. So you find that for line L, you have a point here and another point here. If you connect them, you get the line for L. Similarly, we did for M and N both, and then we have all the three lines here. Now, since the constants are less than equal to type, so we will see which side of the line gives us less than. All the points which are lying on the line will give us 30x plus 50y exactly equal to 1500. So to find out which side will be giving us less than 1500, one simple approach is that you take the origin, which is 0 0, and since 30 into 0 plus 50 into 0 gives you 0, which is less than 1500, so all the points lying on this side of the line, which the side in which origin is there, they will be giving you 30x plus 50y less than 1500. So applying that concept here, we notice that since x and y are to be greater than equal to 0, we have to operate in the first quadrant, and since all these three conditions are to be satisfied with less than equal to type, so we have only this shaded portion, this area, as the feasible solution space. Any point lying outside of this area will be violating one or more constant. For example, if you take a point here, fine, all the technical constants you have less than equal to, but then you notice that x is negative and y is also negative. If you take a point, say here, then x and y are positive, but this particular point is above all the three lines. It means that you don't have sufficient L, M and N to produce that much. If we take a point, say in this region, then this is above M line. It is above this line. It means that you will not have sufficient chemical M to produce. However, this point is lying below L and below N. It means that you have sufficient L and n to produce. If we take a point, say here in this particular region, then here it is below this line, which is n line. It means that you don't have sufficient, you have sufficient n, but since these points are above m and l, so you don't have sufficient m and l to produce. So that way, uh, the points on this space gives us uh, values of x and y, and either all the constants will be satisfied, or in some combinations they may not be satisfied. So the first task is to create two examples of feasible solutions. So obviously we'll have to be in this feasible solution space. So take any point, like say if we take a point here. Now this point is x equal to 10 and y equal to 15. X equal to 10 and y equal to 15. And since this is in feasible solution space, so it is a feasible solution, and you can check that it satisfies all the constants. Like obviously x and y both are greater than equal to 0, and if you substitute x equal to 10 and y equal to 15 in this, then x equal to 10 means 300, and here 50 y will be 750. So you have 1050, that is less than 1500, so that's good. Then 40 into 10 will be 400, plus 30 into 15 is 450, so total becomes 850, which is again less than 1200. And similarly 25 into 10 is 250, plus 300, so 550. So all these constants are satisfied, so this is a feasible solution. Another feasible solution we can pick, maybe say here, which gives us x equal to say 5 and y equal to here it is say 20. So once again, if you check, you will be noticing that all the constants are satisfied. So these are the two examples of feasible solutions. You can have many, in fact infinite number of points are there in the feasible solution space, which satisfies all the constants. Now to pick an example where we have m and n in sufficient quantity but l is not available, so we have to be below m and n line but above l line. So you see this is m line, so we have to be below this, and this is n line, so fine, all these points are below this, so it's okay, but we need to be above l line. So l line is this. Now being below m and above L, so obviously you have this region. This particular area is such area where you have points below M, and M means this particular line, and L is obviously this line. So all the points here are below M and L lines, but M and N lines, but they are above L line. L line is this one. So let us take a point, say we take point somewhere here, means say x equal to 4, or rather 3, and y equal to 32. So suppose we take x equal to 3 and y equal to 20, y equal to 30, say 32, then we can check whether this is satisfying all the constants or not. x equal to 3, y equal to 32. So x equal to 3 means for L you can have 30x is 90 plus 50 into 32 is 1560. So if you add them, you get, let us do the calculation again. 3 into 30 becomes 90, and 50 into 32, that is 1600. So we get 30x plus 50y as 1690, which is greater than 1500, and that is what we are looking for in this area, that constant L should not be satisfied. And as you are seeing that the requirement for chemical L becomes 1690 if we want to produce 3 liters of paint A and 32 liters of paint B. So condition L is not satisfied. You can check for M and N. If we take x equal to 3, then 40x becomes 120, and if you take y equal to 32, then 30y becomes 30y, 32 into 30, so 960. And 960 and 120 becomes 1080. It means that you have sufficient M to produce 3 liters of paint A and 32 liters of paint B. Similarly for chemical N also, 25 into 3 is 75, and 20 into 32 is 640. The total becomes 715, and this condition 2 is satisfied. So x equal to 3 and y equal to 32 is one such example where we have sufficient M and N, but we don't have sufficient L to produce as per that. Now we understand that this shaded portion gives us such values of x and y which satisfies all the constant, and so they are feasible. But then they have different profit values, and we have to maximize, like optimum solution means here we are maximizing the profit. So such value of x and y which are feasible, and also they are giving the maximum profit. Now whatever the profit line be, generally for optimum solution you will find that if you try to increase the profit value, then somewhere at the extreme points, like maybe here or here or here, maybe that you get the maximum profit. Going further, obviously it will be getting into the infeasible area, and you may not have any feasible solution. And if we are below that, then definitely there is possibility of improving the profit value. So normally the optimum solution will be always lying at the extreme points, like this or here or here. Now if the objective function line becomes parallel to the constants, maybe suppose it becomes parallel to this particular constant, then you will have all the points lying between this and this. Means all these points will be giving you maximum, as well as since the objective function line is lying on this itself, it means they will be giving you equal values. It means that you have multiple optimum solutions. Similarly, if the objective function line becomes parallel to this, it lies on this particular line, then again you will have a situation where you may have multiple optimum solutions. Now in this case we are just trying to figure out that to which line the objective function line should be parallel, whether it should be parallel to this particular line, which is L line, or it should be parallel to this line, which is M line. N line is obviously not affecting the object, affecting the feasible solution space right now. So mainly we have to think about the L and M lines. Now here we are trying to change the profit value of B to get multiple optimum solutions with paint A quantity greater than 15. So we will be using this condition to find out to which line the objective function should be parallel. So x being greater than 15, and if you look at the feasible solution space, you find that x15 is somewhere here, and we have to look into a situation where you have multiple optimum solutions where x is greater than 15. So x is greater than 15 means it will be in this part, and you have this line, which is the M line, which is actually restricting the feasible solution space. So if the objective function line becomes parallel to M, then finally when it coincides with the M line, you will have the maximum profit, and if you exceed that, obviously we can't go beyond that, because then we will not have any feasible solution, and below this obviously it is not optimum. So objective function line, if that becomes parallel to M line, then you will have multiple solutions where x value is greater than 15. So we will have to make the objective function line parallel to M line. Now objective function is 500x plus 800y. Now if this has to be parallel to the M line, then you know that the coefficients should be in proportion. So coefficient of x in objective function line, which is 500, then we will take the coefficient of x in M line, because we are making that parallel. So coefficient of x in M line is 40, so 500 divided by 40. Then coefficient of y in objective function line, that we have to change. That is, we are changing the profit value of paint B, which is right now 800. We are changing its value such that the objective function line becomes parallel to M. So we are going to find out the value of this. So here we have a question mark, and divided by the coefficient of y in M line, which is 30. So we will solve this equation, and in fact we will find out what the value should be at the question mark, and that coefficient will make 500x plus 800y coincide with 40x plus 30y equal to 1200, which is the M line, and that gives the multiple optimum solution with x being more than 15. So when you solve, you get that this question mark value should be equal to 375. In fact, you have to multiply 500 by 500 by 30, which becomes 15,000, and then divided by 40, so it gives you 375. So the profit value on paint B should be changed to 375. In that case, you will have multiple optimum solution where the quantity of paint paint A to be produced will be greater than or equal to 15 units. Similarly, if you are asked to change the profit value of paint B such that you have multiple optimal solution with the quantity of paint A less than 10, then less than 10 you can see that 10 is here, and uh, less than 10 means you will have to operate on this side, and then you will have to make the objective function line parallel to this, and which is L line. Then for that maybe you will have to make it parallel to the L line, so you will have say 500 divided by the coefficient of x here is 30, which has to be equal to that question mark divided by say 50, and then when you solve, obviously you will be getting the value of value of profit on paint B, so that you have multiple optimum solution with x less than 10. And if we simplify here, you will be getting the profit value on paint B, which needs to be changed as 500 into 50 divided by 30, which gives you somewhere around 833.33, etc.